Okay. So, next we will come to the thermal resistances, right. So, insulation of, first one you consider insulation of single core cable, right. The thermal resistance of the insulation of a single core cable, it can be determined exactly in the same way as the insulation your resistance, right. So, referring to figure 4, right, just hold on, I will show you the figure 4, this one. Referring to your figure 4, the cross section of a single core cable, this figure only, referring to this figure, right. So, that the thermal resistance dgi of annulus of thickness dx at radius x. I mean, if you consider this, the same dx at a distance ax, right, annular thickness dx, and at a distance x, that your what you call that thermal resistance dgi, G is the capital one, can be written as GL into dx upon 2 pi x. It is, we are representing a thermal ohms per meter, where GL is the thermal resistivity of the dielectric, is about, value is about 5.5 degree centigrade meter for most of the high voltage cables, right. So, this is your thermal resistance. Now, the thermal resistance per this thing dgi. So, thermal resistance per meter length is that gi, capital Gi, you integrate this one, you just integrate this one, then it will be small r to capital R, this figure you think that small r, that is your conductor radius to the external radius r, small r to capital R, right. It will be r to r GL into dx upon 2 pi x. So, it will be GL upon 2 pi ln capital R upon small r thermal ohm per meter, right. So, this is your GI. Now, next is insulation of your for multi-core cable. So, in this case, the calculation of thermal resistance of insulation of multi-core cable, it is very difficult one, because the thermal field is quite complex, right. So, these figures I have taken from somewhere, right. This y axis is thermal resistance per meter per core per meter. So, it is 0.5 to 2.5, and this side some ratio is equal to the total dielectric thickness by your upon core diameter. This side is this ratio, this x axis is the ratio is plotted, that is total dielectric thickness upon core diameter, right. So, thermal resistance of belted cable for a thermal resistivity of 5.5 degree centigrade meter per watt. So, in this case for 4 core cable, this is the red one, for 3 core your 3 core earth one, I mean 3 core grounded, that earth one, it is the black one, upper black one, and 3 core earth, this is unearthed, sorry, this is unearthed, this is 3 core unearthed one, and the bottom one is 3 core unearthed, and this is twin, right. So, double core. So, this is actually from that or what you call from that experimental data, these graphs these figures are taken from somewhere. So, for particularly for the classroom studies or other thing, these equations of this graph cannot be given. So, if any numerical anything is there, data will be provided. So, this is your figure 11, right. So, this figure 11, just now I have written that it shows a set of curve based on experimental result for determining the thermal resistance of belted cable for a thermal resistivity of 5.5 degree centigrade meter per watt, right. So, the value of the thermal resistance as obtained from these curves must be divided by the number of cores before using it for further calculation, because here this x axis, it is actually x axis is the ratio, right. This ratio is equal to actually this is actually ratio, this x axis. So, it is total dielectric thickness divided by core diameter. So, direct mathematical formula cannot be given, but this curve we can use. I mean, if you know this x axis, this total dielectric thickness by core diameter, if you know this one, you can easily find out the other quantity that which is along the y axis, right. So, now protective covering. So, since the protective covering, which is the bedding and serving of the cable, right, is in the form of a cylinder. So, the expression for its thermal resistance similar to equation 31. I mean it is the similar type of expression for this equation 31, right. So, in that case the armor thickness is generally very small and can be neglected. So, we have neglected the armor thickness, right, otherwise it is similar to that. Therefore, thus the expression for the thermal resistance of protective covering is, you are making Gp, P stands for protective, right. So, G2 upon 2 pi ln R2 upon R1 thermal ohm per meter, same equation 31 analogous to that, only G2 and R2 R1 is different. G2 is the thermal resistivity of bedding and serving, its value is about 5 degree centigrade meter per watt. Then R1 is radius over the sheath, that is in meter, and capital R2 is external radius of the cable, that is also in meter, right. Next one will be the soil. The heat transmitted through the cable passes into the surrounding soil. This is understandable, right, because if cable is buried in the cable or even this thing, and that your what you call that heat transmitted to the cable passes into the surrounding soil. In the ideal case of a single cable of external radius R2 buried h meter below the ground surface. Suppose you might have seen the cable laying in the ground, right. If the external radius R2 buried h meter below the ground surface, if the you assume that cable radius is your what you call R2 and buried h meter below the ground surface in a soil of constant thermal resistivity say G3, the thermal field exactly analogous to the electric field. Only dimension is different for various quantities, but it is analogous to electric field between a single overhead line conductor and the ground plane, right. So, the expression for thermal resistance Gs, that is for soil, is therefore derived in a manner similar to the calculation of the capacitance of an overhead conductor with respect to ground. In the capacitance topic, to find out the capacitance of overhead conductor, right, we will use the same expression, right, but analogous to that. Therefore, directly we can write the expression Gs is equal to G3 upon 2 pi ln 2H upon R2 capital R2 thermal ohms per meter, right, where G3 is equal to thermal resistivity of soil, in your unit is degree centigrade meter per watt, and its value actually varies in between 0.3 to 3. So, this is equation 33. So, when you are calculating the current rating of a cable, you have to consider many things. Now, the calculation of current rating, you have to understand here, and you have to compute many things. If the thermal resistances of the different components of the path are known, the current I, which will raise the conductor temperature to the maximum permissible value, can be calculated. Now, the copper loss in the n cores cable, suppose you have a n number of cores, right, each core having a resistance of RAC ohm per meter, say, that means total loss is I square RAC, and you have n number of cores, so multiply by n. So, it will be n into I square into RAC watt per meter, right. So, neglecting the dielectric losses, for example, you just neglect dielectric loss, the cable insulation has to pass the heat generated due to these copper losses. So, that means all these things you have to consider for a cable, right. So, if we assume that the conductor temperature be theta degree Celsius and the sheath temperature be theta s degree Celsius, theta s stands for sheath, right. So, applying thermal Ohm's law between the conductor and the sheath, we have n into I square RAC is equal to theta minus theta s divided by capital G suffix I, Gi, right. So, just we are this thing what we are doing actually, that is thermal Ohm's law between the conductor and the sheath. So, n into I square RAC is equal to theta minus theta s upon Gi. So, now if the sheath loss are lambda I times the conductor, right, copper losses and the armor losses are neglected, the total losses become 1 plus lambda I into n I square RAC, because we are assuming sheath losses are lambda I times the conductor copper losses, that is lambda into this one. Therefore, total losses will be n I square RAC plus lambda times n I square RAC. So, that is why you are writing it is 1 plus lambda I n I square RAC watt, right. Therefore, the protective covering and the soil has to pass the heat generated due to this total losses. Loss means heat will be generated, right. Anywhere power loss means electrical circuit means heat will be generated, and the protective covering and the soil has to pass the heat, right, generated due to this your what you call total losses. Now, let the ambient temperature be theta a degree Celsius. A stands for ambient, right. So, applying thermal Ohm's law between sheath and the ground surface, we have it is between the sheath and ground surface means both Gp and Gs both are coming, right. So, 1 plus lambda I n I square RAC is equal to theta s minus theta a divided by Gp plus your Gs, right. So, in the just 1 minute. So, this is actually your what you call that we are considering both sheath and the protective covering, that is Gp plus Gs. So, this is your, this way you can write. Now, equation 34 and 35, from equation 34 and 35 you can make it like 34 is this equation, this theta 4 is equal your n I square RAC theta minus theta is Gi is equal to 34, and if you will get, I will show you how we are getting n I square RAC Gi plus 1 plus lambda I into n I square RAC bracket Gp plus Gs is equal to theta minus theta. Actually, just for your clarification I am writing this one, that this equation that equation 35 you can write like this, that your Gp plus Gs multiply cross multiply, then 1 plus lambda I, then n I square RAC is equal to theta s minus theta I, right. This you can write. So, now in this equation the equation 34, it is n I square RAC is equal to theta minus theta s Gi. That means this equation, that is your, this is your equation 35 we are getting, from equation 35 we are getting, and from 34 this is from equation 35. From 34 this equation we can write n I square RAC is equal to theta minus theta s divided by Gi. That means theta minus theta s is equal to Gi, then n I square RAC. This equation actually from 34, right. Therefore, in this equation you look, if you look in this equation, theta s is not there, that means you have to eliminate theta. That means theta s is equal to theta minus Gi, then n, then I square, then RAC. This is the thing. This theta s you bring it here, this theta s you bring it here. Therefore, Gp plus Gs, then 1 plus lambda I, then n I square RAC is equal to theta, we are substituting, replacing theta s by this one, theta minus Gi, then n, then I square, then RAC minus theta a. Therefore, this Gi n I square RAC bring to the left hand side. Therefore, Gi, then n, then I square, then RAC plus this all this term Gp plus Gs 1 plus lambda I, then n, then I square, then RAC is equal to theta minus theta, right. So, that is why from this equation, from these two equations, just hold on, from these two equations we are getting, from equation 34 and 35 we are getting that this equation, that your what you call this n I square RAC Gi plus 1 plus lambda I n I square RAC Gp plus theta minus theta. Just now I have shown you. Therefore, from this equation I will be theta minus theta a divided by n RAC. N RAC will be common from both, in bracket Gi plus 1 plus lambda I into Gp plus Gs, it is I square. So, it is to the power half square root. So, this is equation 36, this is the expression of I, but now question is that you have to include also the effect of dielectric loss. So, effect of dielectric loss if we include, this equation will be modified. So, because it is necessary to consider the dielectric losses for cables of 66 kV and above. These losses are independent of load current except in so far as the current causes an increase in the temperature of the dielectric. So, the method is to calculate dielectric loss per meter length at the maximum permissible temperature. Now, you assume that this loss is concentrated at the core. Calculate the temperature rise theta d, which it would produce if it were the only source of heat, and use theta minus theta d in place of theta. Now, because actually meaning is that dielectric loss will be there, right, and we are assuming that this dielectric loss actually concentrated at the core of the cable. Therefore, because of this thing, if temperature rises say theta d, right, then what we can do is in the this meaning is that in this expression we will replace theta by theta minus theta d. So, that means that in equation 36 becomes now everything will remain same, only theta you replace by theta d, it will be theta minus theta d minus theta a, and numerator denominator is same as it is like equation 36 and to the power half, that is square root. So, 37. So, effect of it is equivalent rise of the temperature due to dielectric loss, and that we are considering. So, that means all these things you have to consider for that your what you call for calculation of the current rating of the cable. So, that means in cable different losses are there. So, that will cause the temperature rise. So, there is a maximum permissible limit for the your what you call for the cable temperature. So, that means your current rating has to be restricted till it achieves your maximum current rating, not more than that, right. Next, we will take an example. This example is too long, I have to explain it to you all the data. Long means data, that look all the data are given, then how things can be solved. Suppose a 3-core 11 kV aluminum conductor power in your paper insulated lead sheath belted cable is laid 0.75 meter below ground. Find the current rating of the cable using the following data. Look, so many huge data are given, but things are simple. For example, thermal, I am just uttering all these things one after another. Look, thermal resistivity of soil is given 1.5 degree centigrade meter per watt. Then ambient temperature is 20 degree Celsius. Radius of each core, it is given 13 millimeter, that means 1.3 centimeter. Nominal area of cross section is 400 millimeter square, this is millimeter square. Thickness of the core insulation is 2.7 millimeter, right. Thickness of belt insulation 1.2 millimeter. Outside radius of cable is 40 millimeter, that is 4 centimeter. Radius of cable over sheath 35.2 millimeter, that is 3.52 centimeter. Increase in resistance due to skin effect, it is 3.5%. You have to consider this. Maximum permissible conductor temperature is 65 degrees Celsius. More data are here. Increase in resistance due to proximity effect, 3.5% is taken. The skin effect, proximity effect, all sort of things you have studied, right. So, resistivity of aluminum at 20 degree centigrade, it is 0.02826 micro ohm meter. Then temperature coefficient of resistance 0.004 per degree Celsius. Increase in resistance due to stranding and laying sheath losses 2% each, that also you have to consider, and 10% of total your conductor loss. This is 10% of total conductor loss, right. Then thermal resistivity of dielectric, it is given 5.5 degree Celsius meter per watt. And one more thing is there, thermal resistivity of protective covering, that is 5 degree centigrade meter per watt. So, problem is this much, but data is 1, 2, 3, 4, 5, 6, 7, 9, 10, more than your what you call 15 or 16 parameters are given, right. But calculations are straightforward, data is not a problem here. So, in this case that dielectric loss is neglected. So, neglect the dielectric loss. So, conductor resistance, right, it is cable your this thing resistivity of aluminum is given 0.02826 micro ohm meter, this is given, and cross section also is given 400 millimeter square. So, thermal conductor resistance we are taking that rho L by A, but question is that rho is given, A is given, L is not there, that means it will come in terms of ohm per meter, it will come. So, convert everything with appropriate your unit, particularly in terms of meter or meter square, right. So, it will be 7.065 into 10 to the power minus 5 ohm per meter, right. Now, allowing for the increase in resistance due to stranding and laying, that is PDC at 20 degrees centigrade is given 2%. So, what 2% each. So, stranding for 2%, this thing is given, no, here data is here, that in stranding and laying sheath losses, right, 2% each, that is why it is multiplied 1.02 into 1.02 into 7.065 into 10 to the power minus 5, it comes about 7.35 into 10 to the power minus 5 ohm per meter. Now, RDC at 65 degrees Celsius, in this case the temperature coefficient of resistance is given 0.004 per degree Celsius, this is given. Therefore, RDC at 65 degrees Celsius 7.35 into 10 to the power minus 5 in bracket 1 plus 0.004, and temperature difference is your this thing, that ambient temperature 20 degree and permissible conductor temperature rise is 65, this is ambient temperature 20 degree Celsius and your maximum permissible conductor temperature 65. So, difference is 65 minus 20 is equal to 45 degrees Celsius, that is why this one is multiplied by 45, right, is equal to 8.673 into 10 to the power minus 5 ohm per meter. Now, allowing for the increase in resistance due to skin effect and proximity effect, it is given that your data is given increase in resistance due to skin effect, it is 3.5%, proximity effect also you have to consider, that is 3.5%, right. So, due to skin effect and proximity effect both you consider, right, because here it is given proximity effect increase due to proximity effect 3.5%, due to skin effect 3.5%. That means, this RDC multiplied twice 1.025 into 1.035 into 8.673 into 10 to the power minus 5, this comes 9.29 into 10 to the power minus 5 ohm per meter. Now, total insulation thickness is equal to thickness of core insulation plus thickness of belt insulation, right, both are given, your thickness of core insulation and thickness of bolt insulation. So, it is here thickness of core insulation 2.7 millimeter, your 7 millimeter, and thickness of belt insulation 1.2 millimeter. That means the total insulation thickness will be 2.7 plus 1.2 is equal to 3.9 millimeter. Now, ratio of total insulation thickness to the core diameter, then 3.9 divided by 13 into 2 is equal to 0.15, right. That means, your this core radius, your what you call that your this thing, it is given thickness of core insulation, no, this is that your what you call core diameter, that core outside radius of the cable actually 40 millimeter, right. So, 4 centimeter, and here it is your ratio of the total insulation thickness to core diameter, right. So, whatever it comes, that is radius of each core is 13 millimeter, right. So, diameter will be 26 millimeter, right. So, that means 13 into 2, because this is in millimeter, this is in millimeter, ratio will be dimensionless. So, total insulation thickness is 3.9 millimeter and radius of each core 13 millimeter. So, diameter is 13 into 2, so it is 0.15, right. Now, that is this value, I mean when you will solve the numericals, we will not provide you any graph, but this ratio corresponding to that using figure 11, that 4 different curves are shown, that to get those thermal resistance per core per meter, right. So, suppose a ratio will be given and corresponding data will be supplied to you, even in assignment also, graphs will not be provided. So, thermal resistance per core per meter corresponding to this ratio, this value will be given. If you get this value correctly, then this data will be given, right. So, it is 0.65 your thermal ohm per meter. Now, since it is a 3 core cable, so GI will be 0.65 by 3. You have to be very careful, right. You just do not take your whatever has been given, right. So, it is given your see 0.65, right. So, GI it will come 0.217 thermal ohm per meter, and R2 is 40 millimeter. So, 40 into 10 to the power minus 3 meter. R1 is given 35.2 millimeter. So, 35 point your 2 into 10 to the power minus 3 it is given, 40 it is given, 35 40 it is given, 35.2 it is given, all data are given, right. So, from this the thermal resistance you got 0.65, but you have to see the how many cores are there, accordingly you please divide. So, this is 0.65 by 3.217, right. So, this formula we know Gp is equal to your whatever value, whatever data you have, here it is given Gp, that protective covering, thermal resistivity of protective covering 5 degree centigrade meter per watt, this is given. So, this is actually Gp your this thing is 5 by 2 pi ln your 40 into 10 to the power minus 3 divided by 35.2 into 10 to the power minus 3, this value is given. So, you will get 0.102 thermal ohm per meter. Similarly, Gs it is given 1 point your what you call 5 by 2 pi. So, this value is also in the data, this value is given thermal resistivity of soil, this is for soil 1.5 degree centigrade meter per watt, this data is given. Therefore, Gs is 1.5 by 2 pi ln 2 into 0.75 by 40 into 10 to the power minus 3, same as your before, right. So, it will come 0.865 thermal ohm per meter, and lambda is equal to given 10%, because it is given losses 10% of total conductor loss. So, using equation 36, this equation, right. So, it is given your theta minus theta s, that is the thing 65 minus 20, and whatever values, whatever your this thing data are available, I can show you the formula once again, right. This one, this is general formula, dielectric is not here. So, it should not consider this. So, An into RAC, whatever you got Gi, lambda, Gp, Gs, all you substitute here, whatever you have N you know, RAC you know, because it is a 3 core belted cable, RAC you have computed 9.29 into 10 to the power minus 5 you have computed, then lambda is given 0.1 10%. So, it is 1 plus 0.1, that is why it is 1.1, right, into Gp plus Gs, Gp and Gs we have calculated, this is Gp, this is Gs, that we have calculated to the power half, right. So, I actually becomes your 355 ampere, right, that is your after calculating using equation 36, after calculating this. So, in this problem just I have taken this problem with huge data, such that you will have an idea, actually data are not a problem, only thing is that this formula, right, you have to keep it in your mind that this formula I should use, right. Next is the system operating problems with underground cable. You know that skin effect, Ferranti effect. So, just briefly will be discussed, like your charging current, right. So, system operating problems with underground cables, what are the problems? The first is the charging current. So, a cable, generally for cable is at a high capacitance, even for 11 kV cable you have to consider the capacitance, whereas overhead 11 kV line there is no need to consider the charging capacitance, because it is negligible. So, a cable has high capacitance will result in charging current and reactive power. Suppose if V is the line to line voltage, the charging current you know IC is equal to omega C V, so it is actually 2 omega is 2 pi f c into V upon root 3, right, because V is the line to line voltage. So, the charging current IC can be given as omega C V by root 3, right. So, this is actually per phase, right, because V upon root 3. Now, 3 phase reactive power is root 3 into V into your IC. So, if you substitute IC, actually root 3 will be cancelled. So, using equation 7 you will get reactive power is equal to root 3 V IC. So, it will be root 3 V, then omega is 2 pi f c V by root 3. So, root 3 will be cancelled, and if you substitute IC value here, if you substitute this IC value here itself, you will get it 4 pi square f into v square epsilon 0 epsilon r var per divided by ln r upon r var per meter. Now, so this actually that I mean if you this capacitance, the capacitance expression, right, this has been substituted here. That is why this has come epsilon 0 epsilon r ln capital R by R has come. So, already you have studied the capacitance your what you call for overhead transmission line, same is applicable for cable. So, this has been substituted. So, you got epsilon 0 that is why epsilon 0 epsilon r has come. So, divided by ln r upon r, right. This I am not showing, this is this you know this, right, this I am not showing, but easily you can find out from this expression what is the expression of C, right. So, the flow of charging current causes heating of cable, that is very simple. Therefore, the load current capability of cable is decreased if the temperature rise is not to be exceeded. That means, if you try to fix the temperature of the cable that it should not exceed, for example, if you do not want that cable temperature should not exceed 70 degree or 75 degree Celsius. So, in that case your what you call the charging, it will therefore, what will happen, the load current capability carrying capability of the cable will decrease, right, because if you increase the load current capability, the temperature rise will be there in the cable, and if you do not want, you have to restrict that, right. Thank you, we will be back again.